So I think we'd left off last time. We had solved the essentially differential equation and came up with the voltage in the S domain was equal to IDC, that DC value for the current, divided by C. And then we had in the denominator this polynomial in the S domain, so we had S squared plus 1 over RC times S plus 1 over LC. I don't know if you remember that. That was the answer then to this equation, and I will just answer to the circuit here. There's IDC, and we had a switch that was opened at t equals 0. We said we didn't want to do that in real life. You don't want to short out a current source. That's be bad business. And this was our V of t that we were looking for, right? So we took that circuit. We came up with an integral differential equation. We used the Laplace transform on that. Have you started that in math yet? We're talking about Laplace transform? No? Okay, we'll hope you come up on math pretty soon. We talked about that. We got to take advantage of some things. We got to switch out integration for division and some things like that to make our life easier. And we came up with this expression here. And then we were a little bit stuck because we said, well, we have the answer in the S domain. If you had wanted the answer in the S domain, there it is. But apparently we wanted the answer in the t domain, the time domain. So we left off saying that, well, the next step would be to come up with this in the time domain, which to do this, we're going to have to do the inverse Laplace transform. We did the forward Laplace transform. Now we need to talk about the inverse Laplace transform. So to take it out of the S domain and put it back into the t domain. We went from the t domain to the S domain. Now we want to go backwards from the S domain into the t domain. And this is a common look, a polynomial. There's actually a pretty easy polynomial on top, and then a second order polynomial on the bottom. So this comes up quite a bit. So I'd like to step away from this problem then and look at how we want to do that. So let's, I don't want to think that these are the same, so let's look at a new idea then, or example, because this one's probably not going to be, yeah, I'd like to try this one here. So I'd like to say that my polynomial maybe comes up as something like this: s plus 6 divided by s times s plus 3 times s plus 1 squared. A little more difficult, and it's going to give us a little bit of practice as we talk about doing the inverse Laplace transform, which deals with a partial fraction technique. So let's say that the answer looks like this. It doesn't in this case, but in some cases it does, and we could certainly then apply it to that once we get comfortable with this. Yeah, this is in the S domain, and I'm trying to now get it to the time domain. So what I'm going to do with this to solve it is I'm going to use a partial fractions approach, okay? Because I recognize it has how many roots? 4 roots? Yeah, it should have 4 roots. Okay, so I'm going to talk about K1 divided by S plus K2 divided by S plus 3 plus K3 divided by S plus 1 squared plus then K4 divided by what? S plus 1 taken to the first power. That's the last root. Sometimes it's kind of hard to think about. That's the last one. Okay, and maybe in math class they would write this as A, B, C, and D. Those are the constants. I'm going to write them as K1, K2, K3, and K4. Yes? Yes, this one is squared, and then this is to the first power. Because if I were to rewrite this thing, I would have s plus 6 divided by s times s plus 3 times s plus 1 times s plus 1, right? Yeah. Okay. So I have a root at s plus 1 and s plus 1 squared. Yeah. So that's a fairly standard deal. So if I can come up with the constants k1, k2, k3, and k4, I should be able to get this. And if you want to do some additional research on this, you want to look in your math book, you want to Google it or something, partial fractions. So we're going to do a partial fractions approach. So what I want to do is, I think I will just multiply both sides by s. Okay, so both sides of the equation, when I multiply both sides of the equation by s, I get s plus 6 in the numerator, divided by s plus 3 times s plus 1 squared is equal to k1 plus s times k2 over s plus 3 plus s times k3 over s plus 1 squared plus s times k4 divided by s plus 1. Okay, and let's see. I'm going to evaluate this thing. I'm going to look at it now. Eval when s is equal to 0. Okay, so if s is equal to 0, I come up with a 6 in the numerator there, and then 3 times, what, 1 squared? Okay, so that's equal to 2, which would then be k1 plus 0 plus 0 plus 0. So I can conclude then that k1 is equal to 2. Okay, and maybe some of you can see the problem that's going to come with this, and that's why I wanted to look at this particular one, as that gets a little tricky there. So we got k1. We'll continue on and look at k2. And I won't normally go through this detail. Once you get used to this, you can get through this pretty fast. I'm not going to write out every step, but since we're going through it first time, I will. Questions with that? Okay. This is what you have to look forward to in Math 256. So the good news is, as you prepare for the final in math and the final in here, it's oftentimes all the same. So now I'm going to take this original expression again, right here, and I'm going to multiply both sides by s plus 3. So multiply by s plus 3. So when I do that, I come up with s plus 6 divided by s times s plus 1 squared is equal to, what am I going to have, s plus 3 times k1 over s plus k2 plus s plus 3 times k3 over s plus 1 squared plus s plus 3 times k4 divided by s plus 1 to the first power. So what should I evaluate that at? Yeah. Eval at s equals minus 3. So over here on the left-hand side, I come up with what? 3 divided by minus 3 times a minus 2 squared, which is then going to be equal to, over here I have a 0 plus k2 plus 0 plus 0. So I evaluate that and I get k2. K2 is going to be equal to what? Minus a fourth, I think, isn't it? See, the 3's will cancel, so I have 1. Yeah, 1 over 4, and I'm left with a negative sign, so minus a 4. Okay, well, that seems to be working well. Looks like it might get a bit tedious before we're done, but we've got kind of a methodology now. So what's our next move? Multiply both sides by what? Yeah, s plus 1 squared, great. So s plus 6 divided by s times s plus 3 is equal to s plus 1 squared times k1 over s plus 1 squared times k2 over s plus 3 plus k3 plus, what am I going to have here, s plus 1 squared times k4 divided by s plus 1. And this thing then really turns out to be what? S plus 1 times k4. So then I evaluate this at what? Yeah, s equals minus 1, right? So s equals minus 1, I get 5 over minus 1 times 2 is equal to 0 plus k3 plus 0. So with that, I get that k3 is equal to minus 5 halves. Okay, good. So let's continue on. So I'm going to multiply then. I guess we have the last one is what? S plus 1. So when I do that, I'm going to have s plus 6 divided by s times s plus 3 times, when I multiply by s plus 1, I still have a s plus 1 to the first power down there, don't I? Which is going to be equal to s plus 1 times k1 over s plus 1 times k2 over s plus 3 plus s plus 1 times k3 over s plus 1 squared plus, I finally get k4, don't I? Or do I? So then as we write down this eval at s equals what? Minus 1? We start to see a problem. As we write that, we become very sad, right? Yeah, we're going to have 0 over here, aren't we? Well, I mean, I'm not 0. 0 wouldn't be a problem. We're going to have something over 0. Yeah. So we end up with essentially 5 divided by 0 being equal to, well, I get to cancel one of those, k3 over 0. That's a problem, isn't it? Can't even fix that by cross multiplying. So there's a couple different ways to do that. This. Yeah, we'll get there in a second. I think I did do this. Let's see, this would be 0, that would be 0. I've got k3 over 0 plus k4, don't I? Which still is a problem, I think. Yeah, but you're right. So there's two possibilities, and he's mentioned the second one that I'm going to look at. The first one is probably what you'll see in math books, and it would be to differentiate both sides. Which probably makes you even sadder. Okay, that's not going to be easy to differentiate both sides. You're going to be using the quotient rule and things like that. But it is going to reduce the order on this. Okay, so that's kind of a textbook one, something to keep in mind if this other method doesn't work. This other method that was already mentioned is definitely the best way to go. What we're going to do with this is say that we know K1 is equal to 2. We know that K2 is equal to minus 1/4. We know that K3 is equal to minus 5/2. So we'll plug all of that in. So we can say that we have, so differentiating both sides, this is a lot of work. So we're going to try this, which we'll take all of these, and when we plug those in, I end up with s plus 6 divided by s times s plus 3, s plus 1 squared is equal to, what do we have? K1 over s plus K2 over s plus 3 plus K3 over s plus 1 squared plus K4 over s plus 1 to the first. So I'm going to say then, if I put the values in here, and I think I'll just go ahead and take and plug these in here with s is equal to 1. It's probably as easy to put in as anything. So I have 7 divided by 1 times 4 times what? 4? Square that is equal to K1. Do we have K1? Yep, that's 2 over 1 plus K2 is minus 1/4 over 4 plus K3 is minus 5/2 over s plus 1, that'd be 4, and you square it, plus K4 divided by 2. So this one was not particularly critical. Okay, I just picked a value that was easy to put in. I mean, I probably didn't want to pick one of the other roots. That would be the only thing. So when you go through this, you can solve for K4. And we get that K4, I think, is equal to minus 7/4. Okay? Which is a lot easier than going through the differentiation. Did everyone follow that okay? Okay, let's see where we'll go with this then. So I said that my function essentially in the S domain could be expressed a couple different ways. The initial function, s plus 6 divided by s times s plus 3 times s plus 1 squared, which we then used the partial fractions expansion and came up with this would be K1, which was found to be 2 over s, plus K2, which is minus 1/4 over s plus 3, plus K3, which we found to be minus 5/2, divided by s plus 1 squared, plus lastly what we just found with K4, minus 7/4 divided by s plus 1. Okay, so we could express it that way. So now, making the transition into the time domain. So we need to talk about some values for the inverse Laplace transform. Maybe we'll just come up here with a table. So I'll write down if we have the function in the S domain and what it looks like in the T domain. Maybe I better give myself just a little more room here. Okay, so you could have something like K divided by S plus A, which is going to be K times E to the minus AT U of T. And remember when we were doing the forward Laplace transform, we had something like this, and then came up when we applied the Laplace transform to it to something that looked more like that. So hopefully this is not completely foreign. Sometimes K over S plus A squared comes up. Certainly did in ours. And that's K times T times E to the minus AT U of T. A couple others that come up, we won't work with them initially, but before we're done we'll do them. You will have K over S plus alpha minus J beta plus the conjugate of K over S plus alpha plus J beta. So we had minus J beta and plus J beta. And that gives us something like this. 2 times the absolute value or magnitude of K e to the minus alpha t times the cosine of beta times t plus theta u of t. And lastly, maybe we would have K over S plus alpha minus J beta we'll square this thing plus the conjugate of K over S plus alpha plus J beta. So that one's positive, squared. And that inverse transform would be 2 times the t times the magnitude of K e to the minus alpha t times the cosine of beta t plus theta u of t. Those look a little daunting, but we've got some problems. We'll go through them. They're really not that bad. But for now, is we can really concentrate on putting those to use. Let me double check, make sure I wrote this table down correctly. Okay, I think we're okay with that. So putting these to work in our expression, what are we going to come up with? I guess we'd have one more. Remember the what was the Laplace transform? That the Laplace transform of u of t was equal to 1 over s, right? So with that, if I look at this thing and I want to write the function in the time domain, so I'm going to take this whole thing right here, and I'm going to take the inverse Laplace transform of that. So I'm going to try and write this in the t domain. What's that going to look like? Now we should have, let's see, 2. And that would be u of t, right? So I think everything's going to have a u of t. So let me just write that here. There's u of t. So I'd have the 2. And then what am I going to have? Well, I'd have what? Minus 1/4 e to the minus 3t. Minus, let's see, 5/2. Is that right? Yeah, 5/2. T e to the minus 1t. And then what about the last one? Minus 7/4 e minus 1t. Okay. So that would be what the answer would be in the time domain. It's just the step. That's really essentially what represents opening the switch. Because everything has u of t in it. We had this was 2 u of t, right? And then these had a u of t in them. So I just factored it out.
Hi, Mark.
Mm-hmm.
When we took the s plus 6 over s plus 3 squared, are we going to go through that same process every time we do the partial fractions? That same process to get to that? Yeah,
getting from here to here, we're going to do the same partial fraction routine. Absolutely. Yeah. Well, I probably won't do it in as much detail, because I mean I kind of belabored the thing because we were going through it the first time, but we will go through that process each time. Other questions? So if we wanted to write this is the answer in the S domain. If we want to write it in the T domain, there's the answer in the T domain. Okay. Well, let's try a problem. The previous problem, I don't think that started our discussion here. I don't remember. I don't think I even had values for the resistor, the inductor, and the capacitor. So this is kind of just hypothetical. But I'd like to look at a problem where I actually have those values. And go through this problem from beginning to end. So we're going to start with this guy here. Take this 12-volt source. So in that problem, we've got that 12-volt source in series with a 3 ohm resistor, and we've got that switch. So it looks like we're probably charging up this capacitor. We're going to then open the switch and watch that capacitor discharge across the 2 ohm, the 2 k ohm and the 4 k ohm resistors. So we'd like to find maybe this expression for the voltage across that 2 k ohm resistor. And this is a pretty easy problem. I've selected it for a couple of reasons. One, it's pretty doable, pretty easy to start out with. And two, if we go back and think of fall term when we started this, some of our work in this transient work, this actually works. We could do it as a 6-step problem. It only has one energy storage element. It only has one capacitor. It has a constant DC forcing function. So we're gonna do it with our new technique, and then we're gonna check up on that new technique and check it with our old tools, that 6-step method. And we probably find that the 6-step method in this case is easier, but we will soon see circuits that 6-step method will not work on. So with that, let's get going here. So if I want to try and find the voltage across the capacitor, so let me say that this is the voltage across the capacitor. So if I want to solve for the voltage across the capacitor, I can just open that up, right? So I'm going to have something like this. I'll have 12 volts. And we're going to open this up, the voltage across the capacitor, positive there and negative there. And what's that turn out to be? Essentially, I have voltage division, right? VC is going to be equal to 12 times 6 divided by 6 plus 3 is 9, is that right? So 2/3 of 12, 8 volts. You okay with that? And we could say that this is the voltage across the capacitor at T equals 0 minus is 8 volts before the switch is even thrown. At T equals 0, the switch is open. That's our discontinuity. We're talking about prior to that discontinuity. That's why I'm saying 0 minus. So now we say the switch is thrown, and what's our circuit look like? It got decidedly easier, I guess. So you've got this capacitor here. Once we open that up, the source goes away. We just have a capacitor and a couple resistors, don't we? And we could say that we have positive and negative. There's the voltage across the capacitor. I have 4K and I have 2K. So let me talk about the Kirchoff's voltage law. If I do Kirchoff's voltage law running around this thing, I could have a gain of VC, right? And then I'm going to drop. So let's see, as I go from positive to negative, I guess I could, which way do I want to do this? I guess I could just go this way. Is that going to work for me? Is that going to be a problem? So I could say that I have a gain there, and then a drop and a drop. I guess I could put the current going this way, I of t. So if I went around that way, a drop, so V of c, and then I'm going to have a what? Positive 2k times I of t, and then another positive, what, 4k? Yeah, I think this will work. I of t is equal to 0. Yeah, okay with that. So I've got all kinds of unknowns. Introduce this other unknown. So let me make a substitution here, I of t, and get this back out. What's our governing equation for the capacitor? I for a capacitor is equal to C times dV dt, is that right? So a little general equation there. So we could say that this is equal to the value of the capacitance times dVc of t dt. So when I put this in here, I get V sub c of t plus 2k times the value of the capacitor. What's the value of the capacitor? 100 microfarads. So we have 100 micro times the derivative of Vc of t dt plus 4k times, again, 100 micro times the derivative of Vc of t dt is equal to 0. We're good with that. So let's see. If we tidy this up a little bit, what do I have here? 2K and 4K is 6K. So multiply 6,000 times 100 times 10 to the minus 6. I end up with what? 0.6, is that right? 0.6 times dVc of t dt plus vc of t is equal to 0. So that 0.6, that just comes from 2K times 100 micro plus 4K times 100 micro. Well, that's about as far as I can go, right? So I'm going to use the Laplace transform. So if I take the Laplace transform of this, how do we treat differentiation? This is going to end up as 0.6 times v sub c now in the s domain. I'm missing an s in there, aren't I? You have to multiply it by s. There we go. The one for differentiation? Well, and for a constant. Yeah, so I'm using the one for a constant and for differentiation. So, and then I have to add to this what? So I'll have a minus 0.6 times v of c at t equals 0 minus. So I'll have to deal with that. So that those all come from that term right there. And then what's this one? This is just going to be v sub c in the s domain is equal to 0. This one? Yeah. That's the value at the capacitor before you throw the switch. Yeah. That's part of this whole thing is the rule for the derivative. And let's see, what do we have on this? This actually turned out to be 8, didn't it? Yeah. So we've got 8 there. So I can say that I have that should work. 0.6 s Vc in the s domain plus Vc in the s domain is equal to, see what's this all turn out to be? It's got a negative in front of it. So when I look at this, 0.6 times 8 is what, 4.8? Yes, I'll just move that to the other side at a positive. This is a minus 4.8, so when I move it to the other side, I get a positive 4.8. Okay. So let's see, we've got factor out a Vc in the S domain. That's what I'm trying to solve for. What do I have? 0.6 s plus 1 is equal to 4.8. So V sub c in the S domain is equal to 4.8 divided by 0.6 s plus 1. Polynomial of our polynomial. Really easy one on the top, pretty easy one on the bottom, right? I think I'll, what's that?
Get it back into time.
Yeah, to get it back into time, essentially, I mean, I could say I'm doing partial fractions. It would be a pretty easy partial fraction. I think I'll tidy this up a little bit before I do that. 1 over, let's say, 0.6 times 1 over 0.6. So what's that turn out to be? It gives me what? 8 in the numerator and s plus 1.67 in the denominator. So I could say then that I have, let's see, what am I going to use on this? K over s plus a is equal to k e to the minus a t u of t. So I could go then back in the, this is taking the inverse Laplace transform. So I'm going to say that v sub c in the t domain is equal to 8 e to the minus 1.67 u of t. Well, what were we looking for? That's v of c. I was really looking for this voltage across here, wasn't I? So I need to do voltage division. So I can take this v naught of t is equal to, what do we have, 2k over 6k? 2k divided by 2k plus 4k times e to the, or yeah, 8 times e to the minus 1.67 u of t, which is going to give me 2.67 e to the minus 1.67 u of t. That'll be volts. Well, let's try that. So we'll remember that, or we've got it here on the notes, and let's try the 6-step method. Okay. Okay, so going back to the 6-step method, fall term GE 101. I'll reproduce the problem here.
V naught of t was when capacitor was discharging from the switch is open, correct?
Well, this is for t greater than 0. Yes. So we're opening this. Here's our capacitor. $2K, $4K, and $3K. And as we went through this, remember the 6-step method, we have to find the voltage across the capacitor at t equals 0 plus. So you open that thing up, and what's that turn out to be? The exact same 8 volts that we got before, right? So then you're going to move the switch into its new position and replace that capacitor with that voltage source. So you have that 8 volts there. 4K and 2K. And so we look at this then as V naught at t equals 0. So what's that going to be? Simple voltage division, right? 8 times 2K divided by 2K plus 4K is 2.67 volts. So then what do? We wait for a little time. I mean, this is at t equals 0. Then we're looking at t equals infinity. Like I said, you go back to the chapter reading or your notes from fall term. And at t equals 0, that capacitor looks open, doesn't it? So what's the voltage across here, V naught at t equals infinity? 0? Okay. So then I need to look at, and I can probably get it all on here, so I'll just go up here. If I look into these terminals here, with 4K and 2K, and I look in here, the equivalent resistance, what's that? Yeah, 6K, isn't it? And we know that the time constant then is equal to the Thevenin, or the equivalent. This is going to be your Thevenin, times the value of the capacitance. So we have 6K times 100, this was still at 100 microfarads. So 6 times 10 to the 3 times 100 times 10 to the minus 6 gives me what? 0.6 seconds. Yeah. Okay, so I'm ready to put this together. This piece of information, this piece of information, and that piece of information, and say that we have 0 plus 2.67 e to the minus t divided by 0.6, which if you tidy it up a little more, you're going to have 2.67 e to the minus 1.67 t. And I think that's the same thing. I've got that u of t representing the switch being opened, but we've got the same thing, so that worked out well. So, and you might say, and I think you'd probably have a real good argument that the 6-step method is easier, but it wouldn't take very much to make the 6-step method not possible or much more difficult. And that's actually what we're going to do as we continue on. We've got the rest of the term, which is not that many lectures. We've got Memorial Day off and things like that. So we'll spend the rest of our time this term taking this math technique, the Laplace transform and the inverse Laplace transform, and applying it to circuits. So the rest of our time we'll just be bringing up circuits like this, or quite a bit more complicated, and going through them and making sure that we're comfortable with different situations that come up. So that's where we'll go from there.